Hello and welcome. Look, every single day we are just buried under an avalanche of information, right? Headlines, claims, facts coming at us from all sides. Some of it's true, some of it's kind of misleading, and some is just, well, completely wrong. So how do you build a reliable filter for reality? It turns out there's a toolkit for that, and we're going to open it up and see what's inside. This is the big question, isn't it? It's not about knowing everything, because nobody can. It's about having a solid method for figuring things out. And that's what this is all about. Giving you the core tools, the scientist's toolkit, for sorting what's real from what just isn't.
And right at the heart of this whole thing is this fundamental difference. On one hand, you've got science. It's a tough, systematic, evidence-based process for figuring out how the world works. And on the other hand, you've got pseudoscience. It often looks like science, it talks like science, but it's missing the most crucial ingredient: actual, hard, testable evidence.
Okay, first things first. We need to get our basic categories straight. Let's really nail down the difference between a tested explanation, a fake one, and a belief that, was never even trying to be tested.
The real dividing line here is all about testability. Science, think about how vaccines are developed, is built on ideas that are constantly, relentlessly tested against reality. Pseudoscience, like astrology, makes these huge claims that are often cleverly designed so you can't really test them. And then you have superstition, like a black cat crossing your path. That's not even pretending to be a hypothesis. It's just a belief that's passed down.
And this core idea of using observation and logic to figure things out, it's not new. Not at all. We can trace it way back, over 2,000 years, to thinkers like Aristotle. He was the one who really pushed this idea that we should understand the world by looking at it closely and thinking about it clearly. He basically planted the seeds for what would later become the scientific method.
All right, let's move into the engine room of science. How do we actually formally test an idea to see if it stands up to the data? This is where the whole process gets its real power.
Now this is one of the most brilliant kind of backwards ideas in all of science. To test if something is happening, you start by assuming that nothing is happening. That's the null hypothesis. It's your skeptical starting point. And the entire goal of your experiment is to collect enough strong evidence to say, you know what, I don't think that nothing is happening idea is right anymore.
So, how do we measure our evidence against that skeptical nothing is happening assumption? Well, we calculate something called a test statistic. Just think of it as a single score, a number that sums up how surprising or weird our data is, if the null hypothesis were true. The bigger that number, the more our data is screaming that something interesting is going on.
And here's what that can look like. Now, I know a formula like this can look a little intimidating, but don't worry about the details. All it is, it's just a standardized recipe. It's a way to take the difference you see between two groups, factor in how much the data naturally varies, and boil it all down into that one powerful number, the test statistic.
Okay, so you've got your test statistic. The next tool in the kit, the p-value, tells you what it means. The p-value answers a very specific question. If there was really no effect, if nothing was going on, what are the odds we'd see a result this strong just by pure random chance? A super tiny p-value means your results are really unlikely to be a fluke, which makes you seriously doubt your original nothing is happening idea.
So, how tiny does that p-value need to be? Well, by convention, a lot of scientific fields use 0.05 or a 5% chance as the cutoff. If the probability that your result was just random luck is less than 5%, we get to call it statistically significant. It's basically an agreed-upon line in the sand for making a decision.
Getting a significant result is a fantastic start. But to really understand what's going on, we need a couple more tools. Let's look at how we describe our data and how we frame the question we're asking.
This table clears up something that confuses a lot of people. Okay, so standard deviation, or SD, tells you how spread out your data is. In your one sample, how much do the individual data points vary? But standard error, or SE, is different. It tells you how precise the average of your sample is. It's an estimate of how much that average would bounce around if you did the whole study again and again.
And what about how we ask the question? Well, think of a two-sided test like casting a wide fishing net. You're just looking to see if you catch anything interesting in any direction. A one-sided test, though, is like being a sharpshooter. You have more power, but you'd better be really, really confident you're aiming in the right direction before you even take the shot.
Okay, so we've run our test, we got a result. But wait, was our method, our statistical recipe, any good to begin with?
For that, we need to check the leftovers.
This is where residuals come into play. A residual is just the error for one single data point. It's the gap between what your model predicted would happen and what actually happened in reality. It's the little bit of leftover mystery your model couldn't quite explain.
Oh, I absolutely love this analogy. Think of your model as a cookie recipe. The recipe says the cookies will be perfect in 10 minutes, but if one batch takes 12 minutes, your residual is +2. If your residuals are all small and random, hey, you've got a great recipe. But if they're all really big, or they show a weird pattern, you might need to tweak that recipe.
All right, so you've run a good study, you checked your recipe, you found a statistically significant result. You're done, right? Not even close. Let's look at the final and maybe the most important part of our scientist toolkit. This is absolutely critical to understand. No single study, ever, is the final word on anything. A single result is just one brick. A truly solid, reliable scientific theory is like a fortress, built from tons of different bricks, from many different lines of evidence, all locking together and supporting each other.
So one type of brick is observational evidence. This is where scientists are like detectives, just carefully watching and measuring the world as it unfolds, without getting involved. Think of astronomers charting the stars, or biologists tracking migrations. They're finding the patterns that already exist in nature.
Then you have physical evidence. This is the hard stuff. The things you can literally point to or even hold in your hand. Fossils buried in the earth, the layers in a cliffside, ice cores from Antarctica. These are concrete clues that tell a story about our world's past.
And of course, technology gives us what are basically scientific superpowers. Technological evidence comes from tools that let us see worlds that are totally hidden from our own senses. The incredibly tiny world inside a cell, or the impossibly vast universe of distant galaxies. These tools open up whole new realms of data for us. And the fortress just gets stronger and stronger. We add carefully controlled experiments, complex statistical models, and, this is huge, the process of peer review and replication, where other scientists check your work and try to get the same results themselves. The most bulletproof conclusions in science are the ones where all of these different methods end up pointing to the exact same answer. So there you have it. That's the core of the toolkit. You learn to spot real science from the fakes, you test ideas by trying your hardest to prove them wrong, and you build real confidence not from a single flashy study, but from many different lines of evidence all coming together. It's an incredibly powerful way to think, not just for scientists, but for every single one of us. So the only question is, now that you have the tools, what idea will you put to the test?